I used to sit down and let my mind drift. Most of the time, useless activity, but occasionally it would lead to something that was useful. Yeah, that sort of dreamlike state was very important in my life.
What could be more appealing than highlighting the importance of daydreaming? And also, what could be a more accessible start to a conversation about the science behind the 2025 Nobel Prize in Chemistry than just letting your mind wander?
Sounds wonderful.
There we heard Richard Robson, one of the 2025 Nobel Laureates in Chemistry.
We'll also hear from Omar Yaghi and Susumu Kitagawa, and they're all going to be in this episode where you focus on chemistry and these three brilliant people.
It's a very nice amalgamation of people from very different backgrounds, very different parts of the world, who came together to produce this entirely new world of chemistry.
You're listening to Nobel Prize Conversations. My name is Karin Svensson.
And I'm Adam Smith.
And this podcast was produced in cooperation with Fundación Ramón Areces. Shall we start?
Yes, indeed.
Richard Robson, who grew up in rural Yorkshire, studied at Oxford, Caltech and Stanford, and spent half a century doing research at University of Melbourne, where he laid the foundation of the development of metal organic frameworks. Despite all these achievements, he feels uneasy with his new status as Nobel Prize laureate.
It hasn't been as pleasurable as I would have thought a Nobel Prize winner might have experienced.
Why is that?
I'm reminded of something I saw on television many years ago. Jocelyn Bell, the pulsar lady, was being interviewed. She was talking about the imposter syndrome, which is exactly what I've experienced most of my life. Are you aware of her and this condition?
Yes, I'm very aware of Jocelyn Bell and imposter syndrome. Yes, I remember once a student asking a Nobel laureate rather boldly in a question and answer session after a lecture. It was in Warsaw, and the student said, "Does getting the Nobel Prize make imposter syndrome better or worse?" And the laureate just replied, yes.
Yeah, well, it made it worse in my case. When I was at Oxford, I didn't ever feel like an Oxford undergraduate, an imposter. And this, I think, declined until the middle years when work was going really well. It was very exciting, and I think it disappeared, but more recently it's reappeared with strength. It's something Jocelyn Bell lived with, and no doubt I can too.
Is it because you've been out of the field for a while and so suddenly you're catapulted back into it?
That's a very good point, actually, yes. You see, the prize for me was given for work done more than 30 years ago, and my contribution was more or less complete by the year 2000. And we've done lots of work since, but nothing comparable with what we did before.
Yes, and I suppose you must a little bit feel that it would have been nice to have got the prize some years ago, that it would have been timely, maybe not 35 years after the work, but...
I think I might have been in a better physical condition and I might have handled it all a lot better, yes.
I'm interested that you say that you didn't feel that you were ever belonged as an Oxford undergraduate, or rather that you felt it as an imposter there. I mean, you went on and did a DPhil, and then you went and did postdocs in Caltech and Stanford. And
likewise, the feeling was there, yes.
Always the imposter.
Yes, I mean, never explicitly referred to, never discussed, but they're very central.
And yet, you most definitely are the father of this enormous burgeoning field of metal organic frameworks and porous coordination polymers. I mean, it all stems from your construction of these diamond-like, cage-like molecules that nobody had thought of before. So there's no reason to feel like an imposter. It's your idea.
I agree with you. There is no reason for it, but we're not in control of lots of these things. By the way, I should just say, before we go into anything else and before I forget, that I've been absolutely dependent on crystallographer friends, real friends over the years. Bernard Hoskins, I started to collaborate with in the late 60s and went right through until he died in the early 2000s. all I did was to think of possible structures, think of ways in which they might be made, actually undertake the making of them, get them in crystalline form, which is all really trivial stuff, basically. And the real scientific stuff was done by, as I said, Bernard Hoskins from 1966 to 2002, and more recently Brendan Abrahams, and they come up with all the real scientific information, overall structures, bond angles, bond distances, and so on. So I mustn't forget to pay tribute to them. Extremely fortunate. I don't think I had a crossword with either of them in half a century.
That is quite something to say. What a friendship. Wow. It also says something deep about you, that you're obviously not a person who uses crosswords frequently or easily.
My wife would disagree with you.
So, how important is it to be surrounded by the right people when you're doing research?
Well, I suppose everyone agrees that getting the right environment is incredibly important. But what that right environment is, people differ on. For some, it means they like to collaborate a lot and they want lots of people who are eager to share ideas with them. For others, it means that they just need a place where they can have a small group of like-minded people to talk with and be left alone to get on with it. I think something that is generally agreed upon is that it's really key to have people who test you and your thinking. I've often heard laureates say, try and find people to hang out with who are brighter than you.
But then you have to be able to admit that you're not the brightest person in the room.
Yeah, you do. And one can think of one or two who might have trouble with that. But and of course, you might say that you want to be put to the test, but perhaps there's a happy medium where you don't want to be tested all the time. You need at least some freedom to be right. But yeah, you need a certain amount of humility, but then you need more humility in the face of nature. You mustn't be too invested in your own ideas. That's what we keep hearing from great scientists, that you have to be open to what nature is trying to tell you and be flexible enough to admit you're wrong when you're barking up the wrong tree.
And sort of be open to other people then as well.
Yes, open to what other people have to say, open to ideas coming in, but then not too open. You see, this is, again, it's down to the art of doing it right. Open enough that you listen to people and yet have the confidence to know when you're onto something and other people's advice might be completely wrong. And you keep hearing that in almost every laureate story, there is a point at which they pursued something for which they were told they were foolish. What does it mean to be surrounded by the right people? It means to have people who you can bounce your ideas off. And
who you can also disagree with.
Yeah, that's true. That's a good point. And you learn from as well. And learning to be all the other things it takes to be a scientist, like a leader, which isn't certainly something you ever get taught.
And another one of our 2025 chemistry laureates, Omar Yaghi, also has some interesting thoughts on collaboration.
Yeah, indeed. Let's listen to him talk about working with colleagues and the importance of discussion in science.
Science grows so well when we check each other, when we discuss openly without having to necessarily conclude anything. That's the power of these meetings. That's the power of scientists talking across borders, talking with the rest of the international community of scientists. I think that that's invaluable in achieving rigorous science and creative science. Now, sometimes I tell my students, if you were just working alone and you cannot talk to other people about your work, cannot report it, you probably will not do it. And that's really true. I think we thrive on discussions with other people, and honest discussions are really at the heart of good science.
We could talk for hours about your journey, about the extraordinary difference between the circumstances in which you were brought up and the circumstances in which you find yourself now. And we will talk about it a bit, but were you always a rigorous, thoughtful individual from as far back as you can remember?
I think since I was a child, repetition was so important to achieving a skill. If there was a poem to be memorized or the next day the teacher wanted to hear us recite such a poem, well, I repeated that poem over and over again. The words became more of a project of perfect pronunciation, and you had to do it to recite that poem in a perfect fashion. So it was never good enough until you've repeated it so many times. not just verbal, but even in writing, to write it down so that you have an image of the words in your mind. So the recitation of the poem became part of you rather than just words that come out of the mouth, but words that came out of the soul. And I think that somehow I was blessed with this. And it kept repeating itself in everything that I do. If we have a wonderful result and I'm writing up that result with my student and we're reading, we actually have a tradition until today where for every paper that we write, after the paper is in a readable state, which involved initially many iterations of going back and forth with the student, we all, the co-authors, sit down and we read out loud. We recite that paper all the way from the title to the authors, to the abstract, to the paper itself. And every word and every sentence is up for discussion. Why do we use this word, not this word? Let's look up the dictionary. What is the meaning? What's the true meaning of such a word? And what is the point of this paper? And one of the most difficult things for a scientist to do is to sit down and summarize the results of their projects or their work and actually distill it down to one important point that the whole paper hinges upon. That is such an important part of being a scientist, because that's the message that your reader, especially those young readers, are going to read and say, aha, that was really interesting. So it is a continuous struggle to perfect that paper, and it's a continuous struggle to figure out what is this paper truly about. And so I've developed a set of techniques to try to get that out of my students. For example, I'll say, well, why should anybody on the street care about this work? And then if we were ever unable to figure out the exact point of a paper that should be communicated to the world, I always turn to the student that made the discovery and say, what was that moment in your work where you said, wow, this is amazing, or wow, I think I've got something here, and you got excited? And it's more frequently than not, it's that's the point of that paper.
Omar Yaghi has traveled far, from humble beginnings in a refugee camp in Jordan without electricity or running water, to an illustrious academic career in the United States, where he founded the field of reticular chemistry. It all started when he, as a 10-year-old boy, sneaked into the school library after hours, picked a book at random, and found himself enthralled by mysterious and beautiful sketches.
The point that you got when you first looked at molecules was beauty.
Yes.
It was the first thing about chemistry that struck you, and I believe it's still the thing about chemistry that strikes you, the beauty of it all.
I think so. I think initially it was an escape from my life, and it was really a beginning of a structure. It was a beginning of something forming that I could potentially hold in my own hands and control. And I think I was searching for structure. I was searching for an escape. And so these shapes, they made me feel like I was the only one that found them. Of course, I wasn't. But I held that within me as a way of saying, I've discovered something that nobody knows about. So I kept it secret for a few days until I figured out, well, what in the world are they? But I really do think that in retrospect, that I was searching for structure. I was searching for structure in my life where it displays the chaos and the uncertainty with the certainty of these figures, of these things that seem to be there and represent something solid. So maybe this beauty in symmetry really has to do with structure, the certainty of structure. And so when I became a scientist, I always enjoyed X-ray crystallography, because X-ray crystallography is still the most definitive way of figuring out exactly how things are connected. And so I think that I was in search of structure in my life. Ironically, it was that chaos from the very beginning of my life that made me have this big appetite for risk in research, where I've always felt like I've discovered something now, but what's the next thing? Instead of taking joy in what you've done, I'm already over that. That doesn't mean I stopped researching on it, but I'm just over this great discovery. What is my next thing? What is my next thing? And so I'm constantly taking risks. And so the Nobel Prize has caused let's say, a revolution in my life where I have more energy and more intensity than I ever thought I had. And so I'm thinking about, well, what's my next big challenge that I need to sustain myself by solving the next big challenge?
So your family had been displaced from their village in Palestine in the 1948 Arab-Israeli conflict. You ended up being brought up in Amman in Jordan. I suppose that one thing that might have overwhelmed you was just the desperateness of the situation and the bitterness of everything that had led up to that point. But maybe as a child, bitterness isn't what comes to the fore, it's something else.
Well, I think you find, for me, since I went to a school that had well-to-do kids, the contrast was inevitable, right? The contrast of where I was brought up, where I ended up every day, and the way I went to school, which was sometimes when it was raining, I ended up sitting there in the classroom wet until the last bell rang. While they were delivered in these beautiful, shiny, latest models of cars, and even with chauffeurs, and they have their uniform is nice and pressed, and the comfort of that. The contrast was inevitable. For some reason, I was drawn in to be alone, to do my studies by myself, to find a corner of that room where I could not be disturbed and do my studies. And then when I wasn't doing that, I was sitting there observing all the, large family chaos, whether it's my siblings playing and being rowdy or whatever. I didn't participate in any of that, which was very strange. And in fact, at some point, my siblings and my parents discovered that if anybody came close to me, they regretted it because I was very sharp at telling them to just go away. And, with my parents, and in third grade, I told them that I do not like them to look at my grades. I basically threw a fit and foamed probably at the mouth. And I said, absolutely, I will not show you my grades. I want you to leave me alone. And I think that also was a way for me to internalize a lot of the things that were happening around me. With the grades, I thought it was a matter of pride that my parents should trust that I'm doing the best that I can to do well in school. And I think after a while, they realized that maybe there isn't anything wrong with this child. It's just he wants to be left alone to do things on his own, a pretty independent kid. Again, that's another thing that has contributed to my later in life to take new paths in research and to try to address big problems that everybody else said, couldn't be done.
And your parents placed that trust in you, which is so key.
Well, they had so many kids. I think they just had no time to deal with this odd kid. I think that they went away thinking, well, look, he doesn't cause trouble. Clearly, he's doing okay in school. So what else do we need? Yeah.
Susumu Kitagawa is a pioneer of porous coordination polymers. Growing up in Kyoto, he dreamt of becoming a scientist so that he could learn to control the weather, because he didn't like when school excursions were cancelled due to rain. In his science, he is guided by those who came before him in the Japanese research community, and ancient philosophical concepts, two things we will hear more about in this episode. When you spoke to Professor Kitagawa, you started by showing him a piece of art. What was it?
It was a piece of calligraphy. It was a picture of a framed piece of calligraphy hanging in a small restaurant in Kyoto, and it was drawn by the Japanese chemist who was the first chemist in Japan to be awarded the Nobel Prize, Kenichi Fukui. And it turns out that exactly the same piece of calligraphy, also drawn by Fukui, hangs in Kitagawa's office. So it has a resonance to him. I knew that the concept mattered to him. I didn't know that he had exactly the same thing in his office.
And who was Kenichi Fukui?
He was a chemist, a theoretical chemist who worked on the mechanisms of chemical reactions. In some ways a mentor to Kitagawa in his approach to research, as were other Japanese laureates who have this particular interest, I think, in philosophical concepts of research. For instance, Hideki Yukawa, who was the first Japanese person to be awarded the Nobel Prize in 1949, the Physics Prize for his prediction of the existence of mesons. Again, an influence on generations of Japanese scientists. But let's listen to Susumu Kitagawa himself explain the meaning of that piece of calligraphy. I think the characters say chi ji zai, but what does this mean?
Yeah, chi means wisdom. Jizai is the freely we create or use. The background is the Buddhism wisdom.
Right. So yes, it's a very ancient concept.
Yeah, traditional.
But how would you interpret the free use of wisdom? What does it mean to you as a scientist?
Yeah, in my case, before I'm talking this, Professor Fukui said another thing. In a traditional wooden statue in the Buddhism shrines, you can see very fantastic, powerful statue. So, long time ago, the very, very genius artist, his name Unkei. Unkei used the hammer and this kind of the, knife, something.
Chisel, yes.
He made this kind of things. So, Professor Fukui said, he did not create this kind of statue. Just dig out. That means the nature already has the laws and mechanisms and theory. Fukui sensei told us we are just making action or carrying out this kind of science.
That's beautiful. So just like the sculptor, you're removing the extraneous matter to reveal the inner truth.
Yeah. This sculpture is buried in the wood. So just dig out. The science like that, he said, because his background in quantum chemistry and also the theorist. So nature already has the rules in everything. So the theorist just dig out and get this general rule, something. Also, to do this, chi-jizai, wisdom, this is very important. That's my understanding. So this kind of the fantastic notion, just I thought we should carry out our chemistry just after the curiosity. That's very important. We don't think about just application. This is useful, something like that. No. Our curiosity is, for instance, two atoms, two elements. What kind of materials we can make? In that case, that is my curiosity. And also the nature always had rules. We also have seek the new rule and the new recipe. I mean, I'm an experimentalist to getting a recipe. Not all, but most of the part, I follow his thinking.
It's absolutely fascinating. The jizai is basically allowing yourself to freely follow your curiosity without restriction and see what rules you can uncover. This, of course, is also fundamental to the makeup of Kyoto University and its whole way of being, right?
Yeah, I think so. The curiosity is very, very important concept in our academia system. The student had a very crazy idea many times, but I enjoyed very much listening to what they are thinking. It's a kind of academic freedom. Without freedom, they did not tell me what they are thinking. The professor is so the authority, and just like this, it's very difficult to get the free idea, the curiosity to express their very interesting, curiostic ideas. So this relationship is very important.
Is it common for Nobel laureates to be so entrenched in philosophy?
That's an interesting question. I don't think it is really, at least not overtly. It's common when you talk to Japanese scientists. They seem often to talk openly about some of the guiding principles behind their approach and that ability to think openly and flexibly about things. But I'd say that in general, it's not something that scientists in the West, at least, do talk about very much. The impression I've had is that it's all bound up with the idea of what is the art of doing good research and choosing good questions and making the right choices. There's a philosophical component to it, which is described in terms of making choices in science. But the wider issues of the philosophy of science, I don't think they think about so much. And I think that's probably something that is slightly missing, that if you bring research scientists with philosophers of science together, often there's a kind of crisis of semantics where there's perhaps a lack of understanding. I mean, it's like when you bring a philosopher together with a scientist to discuss the topic of consciousness. The understanding that those two groups bring to that topic is so widely different. It's really very hard to even begin the conversation when they're in such different places at the start.
Well, there is the common theme of thinking deeply about something.
That's true. It's a common theme. They'd both see themselves as questing for some truth. In my conversation with Richard Robson, he also talked about thought processes that go beyond what one might expect from one's conception of what is a standard scientist.
I used to sit down and let my mind drift. Most of the time, useless activity, but occasionally it would lead to something that was useful. Yeah, that sort of dreamlike state was very important in my life. I wasn't sort of aware of it at the time, but I am now.
It's a very important point. I suppose it just happened for you naturally, but how did you create your thoughtful moments? Did you isolate yourself? Did it just happen any old time of the day, or?
I guess I did isolate myself, yes. But almost dreamlike. And as I said, a lot of the stuff that I was dreaming was nonsense, but that was continuous in my earlier and middle years. I sometimes achieve it nowadays. I mean, it's not something you can try to do, but just occasionally in the last 20 years, I've entered that sort of state again, but less and less frequently, I must say.
What do you do with these ideas? Do they just sit in your head, or do you write them down?
Write and scribble them down in handwriting that I can barely understand a week later. But yeah, even now I scribble things down.
You said one of the questions that has always driven you is the question of what if?
Yes, indeed. That's where a lot of these useless thoughts arose, it's really stupid things. But I'd continue. This is all very restful and dreamlike.
But it's great. It's a lovely question, what if? You can think of so many things that would be better if people would only be a bit more imaginative about the possibilities.
I don't worry about it, but I can't help thinking that younger people are driven. I had lots of contacts of people who want to know what they need to do to become a Nobel Prize winner. It really never entered my head until my boss at the time, Tony Wedd, came along and suggested that he might nominate me. That was many years ago. Never entered my head.
No.
And now people want to deliberately set about the process of doing this. I think they're wasting their time. Anyhow, this dreamlike state was really important in all of this.
Were you doing it even as an undergraduate? Had it begun at an early age?
Yes, I think so. But particularly when I became a postdoc, yeah.
I'm sorry to go on about it, but I agree with you that I think it is something that everyday life these days tends to militate against. I think it is worth exploring. I know that you don't like giving advice on any aspect of doing science, but if I pushed you to give advice on how to reach a dreamlike state, what would you say?
I have no idea how it happens. I couldn't give advice about how to achieve this state. In fact, I'm not able to achieve it myself nowadays.
Right. But it's something to do with just letting your mind free, I suppose.
Yes, that freedom from stress. And I've been very fortunate at the University of Melbourne from that point of view. The conditions I've lived under have been ideal for me. Very little interference, really, in what I was doing and what I was thinking. And I don't think younger people have that privilege nowadays. I went many years before. I never thought of. I started as a lecturer, and I think I thought at the time, I'm quite happy to be a lecturer. And my boss at the time after several years, came along and said, did he think I might make an application to become a senior lecturer? I wouldn't have thought of it if he hadn't come along. How did I get onto all of that?
I really think that's extremely important, Richard. I mean, it seems to me that, in fact, all three of you who share this Nobel Prize came into your work in a rather sort of unambitious way, that intellectually ambitious, very ambitious in terms of curiosity, but not so much career building. It was certainly not in your case, as you've outlined, and Professor Kitagawa was really very much influenced by the Japanese scientists who'd gone before him, Japanese laureates who'd gone before him, who advocated a very curiosity-driven, free approach to information gathering, thinking only about really the fundamentals of nature that you're trying to uncover. And Omar Yaghi was building a career slowly with low ambition. He said, his greatest ambition when he started out was just to publish one paper that had 100 citations. That seems to have given you all three of you, the freedom to properly explore and not be rushed and to delve as an ideal scientist might. I think it's extremely important.
I do too, but it's not the way things are going at the moment.
So let's talk about the science. What was the discovery that these three laureates were rewarded for?
Well, they developed an entirely new area of chemistry, which are now called metal-organic frameworks. So these are crystalline materials which, at least at the outset, were combinations of metal ions separated by organic linkers, carbon-based linkers. They were open structures, so they contain lots of spaces between the metal ions and organic linkers in a very regular pattern. And they turn out to be incredibly useful, although the reason that all three of these laureates began working on this was nothing to do with application and all to do with just interest in structure.
And these MOFs, as people call them, what are they good for?
Well, because they have these holes in them and they have an enormous internal surface area, they can be used to absorb molecules from the surrounding medium, water, air, and store it. And because you can design them in so many different ways, you can tailor their shape so that they selectively pull out particular molecular shapes and properties. And that means that you can have them take carbon dioxide from the atmosphere or heavy water from a mixture of ordinary water and heavy water. Many, many different potential applications. It's a whole field of what they like to call reticular chemistry. In other words, chemical molecules that look like nets and can fish things out of the medium and then give them back when you want them. So, for instance, Omar Yaghi has come up with a solar-powered box that can give you fresh water from desert air.
Wow. You also mentioned porous coordination polymers. Is that the same thing? Or
Yes, pretty much. They are, again, crystalline materials based around these regular structural elements. But I suppose strictly molecular organic frameworks are a subset of porous coordination polymers because the porous coordination polymer doesn't have to be a 3D structure.
It's so interesting that this is sort of all about the importance of the spaces in between.
That's very true. It's so appealing that what starts out as looking like something totally uninteresting with no apparent use turns out to be where the treasure lies.
And we will hear from Susumu Kitagawa connecting these voids with the philosophical concept of the usefulness of the useless. Where does this idea come from and what does it mean?
Well, actually, until I talked to Susumu Kitagawa, I was quite content to say that idea came from a book published in 1939 by an American called Abraham Flexner, which was called The Usefulness of Useless Knowledge. And in that book, he makes a very strong case for the fact that the things that we all depend on, the applications that we all need, arise from people studying things that have no apparent application at all at the time. And these are studies pursued purely for interest's sake. And so he's arguing passionately for the need to support research into fundamental concepts that people are interested in without really thinking at all about what it will be used for in the future. But Kitagawa pointed out to me that, Abraham Flexner is just a new kid on the block. People have been thinking about this a long time. So 2,500 years ago, the Confucian philosopher Changzu was talking about exactly this, the usefulness of useless knowledge. Talking, for instance, about bits of the tree that people just discarded, thinking that's only good for firewood. But actually, in the end, that piece of the tree that you thought was no use, that's what you need to hold up your house, for instance. And making the same point, that thus study without application, just pure application of your interest, is well worth pursuing. I asked Susumu Kitagawa about being drawn into studying not what he was expected to study, but the spaces. Let's listen to him talk about that. You took this brave decision to study the spaces in the structures you were investigating, and that the spaces were thought by pretty much everybody else to be uninteresting. They were interested in dense materials, and you said, well, yes, but there are pores and we should be interested in those. I can see how that ties in with the philosophy of free thinking and trying to understand the rules.
Free thinking and also the usefulness of the useless.
Yes, without so much a thought of the usefulness, but rather just a thought of let's investigate the apparently useless. Yes.
Yeah, because that time I looked for the highly dense compound because I was interested in the electric conductivity. So for this, we need to have the electric conduction path. So if we have the space in between the entity, atomic and the molecular entity, so no way to go for electron and the charge. So we did not think about the space or void.
Yes, why would you want a void?
Yes. And so we studied the synthesized various crystals and see are there any electric conduction pathway. So one day I went to the Kyoto University Computer Center because in the Kindai University we don't have this kind of good system. And we have the data. So they just input data and they calculate. This is a trial and error calculation. Mm-hmm. We set up one model and just check this is okay or not in comparison with observed data. But early morning, it's easy. Several people just using this one. But this is computing system very fast. But to input data, 1,000 card, just the computer should read it. So it takes a long time. And almost the noon, the many people come to input, long queue. So it takes a long time to get our turn. So we have plenty of time. So we discuss about this structure, that intermediate case. And my student said, oh, Professor, this has a cavity.
It's lovely to hear the birth of the idea, standing there waiting at the computer, waiting to input your program cards.
Yeah.
And there it was born. Of course, the important point is that you recognized that there was something there, that it was something totally unexpected, totally different from where you were heading. And you had the good sense and the preparation and the curiosity to change direction.
Yeah, the curiosity with the usefulness of the useless. Void is useless.
Would you advise people starting out in research to actively search for the useless, or is it something that you just have to have in the back of your mind, always to be alert?
I encountered this notion after Professor Yukawa's book. Mm-hmm. He introduced Chansu, in particular, and he likes usefulness of the useless. So he said, this usefulness of the useless is a thought of creativity, because everybody knows usefulness. So that means a researcher doing this chemistry means a follower of pioneer. Bad things is follower. But useless things, nobody focusing on that case. If the person who are interested in the useless thing, that means no follower, just a pioneer route. So anytime the young people should think about that. If this chemistry is the pioneering work, that means nobody supports that time. Or many people support this, or the young scientist is coming in a big field. There's a big competition. That time it looks like their feeling is, okay, I am very exciting to do something. But this is a way of the follower or pioneer. So that's a point is very important for the young people to think about that.
Well, that's the question, isn't it? To follow the pack or venture into the wild.
Yes, I don't think many Nobel laureates are pack animals. You've got examples of extreme thinkers like Barry Sharpless, who's been awarded the Nobel Prize in Chemistry twice. And he just seems to relish taking dangerous turns. We don't know how many he takes that don't lead anywhere. We just see the ones that come to fruition.
Or how many Nobel Prizes he's still got in him.
Yeah, quite so, yes. By the time he was awarded his first Nobel Prize, he was absolutely on the way to his second, that he was already developing his next concept. Yeah, go in his lab and take a peek now. That's an extreme form of living dangerously in your head, having wild thoughts and seeing if you can make them come right. Someone like the pair Barry Marshall and Robin Warren in Australia, who worked out that most stomach ulcers were caused by a bacterium in the stomach, Helicobacter pylori, which was against all conventional wisdom. That wasn't a very popular avenue to go down. They saw evidence that they thought was enough to go on, but it took them a long time to convince themselves and convince everybody else. Having the confidence that you've seen something that makes the risk worth it. I suppose, in a sense, Omar Yaghi is one of those brave explorers who went against the grain when he decided to pursue an interest in strong bonds rather than the weaker bonds that most people were interested in. Let's listen. One of the things in your approach to chemistry is that you seem to have been able to see through preconceptions. They don't worry you. So, for instance, as a young researcher, you quickly gravitated towards building strong bonds, whereas almost everybody else was focused on weak bonds. And people didn't believe that strong bonds would get you anywhere, but you somehow felt they would. What gives somebody the possibility of seeing through everybody else's kind of miasma, everybody else's inability to see? Is it the outsider's perspective? How were you preconditioned, do you think, to see things differently in chemistry?
Well, I think my father's teaching was always to try to develop your own thing, try to break new grounds. Even on a small scale, there was a question of don't do it like everybody else does, try a better way. And this message was also reinforced by my PhD advisor.
Walter Klemperer.
Walter Klemperer always said to me, don't be an ambulance chaser. Break your own grounds, think independently. Think about what you could do that nobody has ever thought about. So I think that message was reinforced. I was always also inclined towards doing things that others, for example, when I went to do my postdoc with Dick Holm at Harvard, he was heavily pursuing bioinorganic chemistry. In fact, people say he was one of the founders of that field. Well, bioinorganic chemistry involves metals and organics. And I said, I don't want to work with anything organic. I want to do something completely inorganic. So we had to invent a project around that. And it was the only project of this kind in his whole group, which was a group of, 24 researchers. So I was always searching for something different. And I think that this business about building structures from molecular building blocks was one of the challenges that I wanted to see if I could do it. Could I build structures from? And then when we started doing that, to make them useful, we realized you have to build them from robust bonds. And that's when you hit the wall of crystallization. It's that you need to crystallize these things because nature, when you put stuff together, nature wants chaos, creates chaos. And that's molecules are no different. So I think that was really from an inner desire to do something different, to do what everybody else said couldn't be done. It was really taken as an article of faith that you will not be able to crystallize structures that are assembled from strong bonds.
It's a bit of a gamble because on the one hand, you say you've got to make a success of being an immigrant in America. You mustn't fail. You can't go wrong. So my approach to that is I'm going to try something really bold that could absolutely fail.
I separated my scientific life from my personal life. And it's a bit of a tension, but I have always done things that made sense scientifically to me and enhanced my scientific objectives, regardless of what my family felt would be better. So, for example, when I finished my PhD, I called home and I said, I have a PhD in chemistry now. And they said, well, what's your next step? Are you getting a job? And I said, well, it's sort of a job. It's called a postdoc. Well, how much does it pay? Well, that doesn't sound like a real job. And so they couldn't understand that, but yet I wanted to do that. And when I was looking for jobs, I was offered job in industry for $85,000 a year. Very lucrative, and I would have certainly taken at least half of that and sent it back home. But I chose a job at Arizona State University for much less than that, for $38K. Again, that separation of what the stress or the tension that is resulting from personal life, family life, and the fact that science must move forward. And the way science moved forward is by trying to address big challenges. It gave meaning to my life. It gave me a sense of worth. It gave me something to look forward to. And at the end of the day, yes, I did say to myself, well, if I fail, then I won't get tenure. But then I can just get a job in industry and make that big fat salary. I wouldn't like it, but nevertheless, that's my fallback position. The other thing, over the years, I try to mitigate that risk a little bit by having projects that I call potboiler projects, where a student that has a very difficult project at least can rely on this other project to yield results so that they don't graduate without a paper. I think it's our moral obligation to make sure that students are not sacrificed over extremely difficult projects that may not yield in their graduate student lifetime.
One aspect of all this that is, of course, of great importance as governments and everybody else try to get scientists to address global challenges, and scientists indeed want to address global challenges, is to ask whether you had a game plan that would get you to major applications that would help humanity, which is where you've ended up, or whether it was you were just following your instinct and your interest and, in a way, having fun with things and hoping that it would work out. I suspect the latter. I suspect there wasn't a great plan behind it all.
No, when I started out as an independent scientist, my dream was to just get in a lab and make something beautiful, beautiful crystals, beautiful structures. In fact, I didn't want to deal with society and societal issues. I deeply thought that societal issues are not for me to solve, that in fact, I am a scientist and I am pushing the frontiers of science. And these frontiers of science could potentially be used by others to help society. I felt like my job should be unbiased by societal stress or by societal needs. I felt like as a scientist, I can do my best job by investigating science for the sake of science and for the sake of creating new knowledge that potentially could help solve problems down the road. But I didn't feel like solving those societal problems was really my concern. That is until we discovered MOFs, and we were making lots and lots of them. And the CEO from a major chemical company in Chicago, an alcochemical company, his name is Ron Elaine, came to see me to see what is all this noise about with MOFs. And I was showing him models on the computer, real physical models in my hand, and I was like a kid in a candy shop. And he surprised me by his question, which was, what are they good for? And I said to myself, what a ridiculous question. I'm a scholar. Okay, scholars do not have to think about what their creations are good for because we're advancing the frontiers of knowledge. And that body of knowledge adds to other bodies of knowledge, and in the end may very well change the way people think and so on and so forth. He said to me, you can be an excellent professor doing what you're doing, but you'll never be a great professor unless your work ends up benefiting society, unless these MOFs reach society and build solutions to problems and build new economy. That was interesting. So it helped that he gave me a grant and a little bit of consulting fees. And I thought, okay, maybe I should listen to him. But I think then my thinking became that it is our obligation to go beyond discovery and to take those discoveries all the way to society because society paid for them in the first place. So on one hand, you want this acquisition of knowledge to be done unbiased by societal needs. But when you discover something and you think it's significant, you should push it all the way to benefit society. And I think that that's the beauty and the satisfaction of doing science.
The applications are pouring out. Recently, you've been much talked about because of the very important ability to extract water from air and the usefulness of being able to do that at scale in crisis situations. There's, of course, scrubbing the atmosphere of carbon dioxide is another thing that is coming out of MOFs, and there are many, many potential benefits to come. Do you see your role as being to live on the application side of it now, or to create new possibilities? And where are you these days?
Well, I have startups that are trying to commercialize these aspects that you discussed. Water harvesting is very, very close. Everything looks good in terms of the energetics, the water being clean, the devices operating under low humidity and high relative humidity. Everything looks fantastic. The most energy efficient devices for harvesting water that would be out there, and generating water for drinking, for household use, for cooling down data centers. All these things are on the table, and they are real possibilities now because the MOF works, the device is working, and they can work for years. The MOF can last for 6-7 years, maybe even more, but it's graded for 6-7 years, at which time, when it, let's say, quits working, we can separate into its component and reassemble it in water with zero discharge process. So very, very exciting progress that we are making with water. I think with CO2, we showed that scientifically the problem is solved. And the scale required to address the problem is commensurate with the scale that industry works on. We just need to recognize this is a crisis so that we can put sufficient investment in it to make it a real solution. So that's one of the aspects that I'm working on.
We've talked about the exciting applications of MOFs, but as we've just heard from Omar Yaghi, this focus on application isn't always appreciated by scientists. Why is that?
The easy answer is to say that a focus on application can potentially constrain thinking, I suppose, that so many discoveries have come from having long-term freedom to mull over a problem and consider it from many angles and eventually come up with some understanding which didn't have any obvious use. And that then the application has come. And if you'd been told from the outset that your job was not to do that at all, but rather to come up with a cure for this disease or whatever, you wouldn't have had that freedom. You would have been too concentrated on the job, and it takes both sorts. But, for instance, Omar Yaghi, at the same time as talking about the fact that he approached this topic because of the beauty of the structures he was making and with no thought of application, also feels it's beholden on scientists to deliver application when they can. I suppose it's also timing, and it's also recognizing what you have to offer at a particular moment. You said application isn't always appreciated by scientists, and I think that is precisely right. It isn't always appreciated by scientists. It's appreciated at the right moment. And when that moment comes, you should grab it and do something with it. It's your duty as a scientist to help this discovery, help people, help the world. But that's not always what's happening. There are times when you're not doing that. That is not your modus vivendi. You should be indeed ignoring application because this isn't the moment for applications. This is the moment for thinking about the fundamentals.
And Susumu Kitagawa has some very firm views on this. Let's listen.
There have been multiple generations of porous coordination polymers. The possibilities are expanding extraordinarily fast. And so application has become what everybody is focused on. But for you, what is the most exciting thing about how porous coordination polymers have developed? What are you most pleased about?
My stance is very clear. Just I said the curiosity. So that means I do not care about application. So I have to define the application. Fundamental science, for instance, we synthesize new materials. So new materials contains two meanings. First one is the new framework, new topology, which the Omar Yaghi developed, reticular chemistry. And another one is a function, new properties, which I was so interested in and developed this one. And the big function is just a softness.
The flexibility.
Yeah, nobody think about that. So my focus is not application, just function, new function. For instance, 2 years ago, we did the separation of D2O and H2O, heavy water and light water. Natural water contains only 150 ppm D2O, very low concentration. This situation is just like the CO2 separation from the air. CO2 also 400 ppm. So I was so interested to just recognize these all in a huge amount of the light water. So this is my focus like that, the function, new function, not application. But after my work, several people and the company, they try to scale up and something like that. So my role is just a focus in the fundamental.
Yes, that heavy water separation is an absolutely beautiful, beautiful thing to be able to do, unimaginable before.
So many things we have to challenge.
But the distinction you make is so important and subtle between function and application. It must be so easy to get distracted into really going full speed ahead with the application, and industry comes in and everybody is excited. But to maintain this focus on new function.
20 years ago, it was a very hard task for me because the government and the companies, all the people just expect this application. It's very difficult. In the case of application, means equal scaling up and also the cost down. Otherwise, it's not realized. So it's a very tough time. But right now, I'm very happy. There are so many startups. Startups can make a lot of the MOF materials based on the recipe, our recipe. Just modify this recipe and scale up and the cost down and directly this given to the company. Yeah, it's kind of different role.
Yes, I mean, it's seeded so much, but that leaves you free to continue. Mm-hmm. And now it's easier for you because now in the tradition of Fukui and Yukawa, you're a Japanese Nobel laureate and it's an easier ride.
Yeah, and what is interesting, the Yukawa and the Fukui sensei, all these scholars are theorists. So in a sense, they have the pencil and the paper. That's enough.
And in Fukui's case, he has the brush. Do you also do calligraphy?
I have no experience, no rich experience using the brush. Nowadays, I use this kind of pen.
A whiteboard marker.
I like the writing this one, usefulness or useless, in Chinese character. Many people ask me to give me your signature and your very best writing, usefulness or the useless, and my name.
I think I will probably join the line of people asking you for such a thing when I meet you next. It's been an enormous pleasure to speak. Thank you very, very much indeed.
Oh, thank you. A very enjoyable discussion.
Thank you, Adam. Thank you for this great interview. You always get a lot out of me that I wouldn't have discussed. So thank you very much.
Thank you very, very much indeed for this conversation.
Thank you too. And I do hope you can salvage something out of that nonsense that we've... Anyhow, I hope so.
That went well.
You're the one to judge. I'm just the one to try and make everybody tell their best stories.
See you next time.
Indeed. Look forward to it.
If you'd like to learn more about the 2025 Chemistry Prize, don't miss this episode's show notes. There we help you explore the science and the minds behind the medals with articles from nobelprize.org. You can also relive the excitement of the prize announcement or the pageantry of the Nobel Prize award ceremony in film clips from our YouTube channel. Don't miss it. Nobel Prize Conversations is a podcast series with Adam Smith, a co-production of Filt and Nobel Prize Outreach. The producer for this episode was me, Karin Svensson. The editorial team also includes Andrew Hart, Olivia Lundqvist, Monica Miller and Simon Doyle. Music by Epidemic Sound. You can find previous seasons and conversations on Acast or wherever you listen to podcasts. Thanks for listening.